Hi everyone, this is Frank again. Welcome back. Today, or in this little short video, we would like to discuss or have a small discussion on the theory of thermal conductivity in liquids. And basically, as of now, the theory has been developed for half a century ago, but actually it's not yet been possible to be implemented for practical calculations. Okay, so we're just going to introduce a very rough theory. This is the theory developed by Brigmans. It's called the Brigmans simple theory of energy in pure liquids, or energy transport in pure liquids. So let's put the transport back. Energy transport. Okay, and Brigman has the first big assumption is that he assumed that the molecules in the liquid are arranged in a cubic lattice. Okay, so molecules are arranged in a cubic lattice. Meaning that molecules are kind of packed like a crystal, right? So if you think of a cubic lattice, the most common one would be something that looks like this. So this is a typical cubic lattice. Okay, and the center-to-center spacing, which let's draw two cubic lattice. So the center to center, meaning the center is right here, from the red dot to the red dot, this spacing is assumed or given by the formula V over N to the 1/3 power. Okay, and the V over N here, the V over N here would be the volume per molecule. Okay. And the second assumption, let's put 2. The second assumption is that this energy is transferred from one lattice plane to the next at the sonic velocity, so the speed of sound. So let's use V sub S for the given fluid. Okay, so using these two assumptions, Brigman basically just tried to reinterpret the thermal conductivity we just derived in dilute gases. So let's recall that for dilute gases, what we have is that the thermal conductivity K equals to 1/3 times the density times the constant volume heat capacity times the molecular mean speed and the mean free path. Okay, and we can also write that as what? As equal to the density times the constant volume heat capacity times some characteristic velocity and some characteristic length A. Okay, so you can see that we modify the mean speed to some characteristic velocity, and we modify the mean free path to some characteristic distance. Okay? So, what's next is that let's look at these values one by one. So maybe we should put this like that. So this is assumed for liquid. Now, the heat capacity for a liquid at constant volume is about the same as for a solid at high temperature. Okay, so the heat capacity or the constant volume heat capacity C sub V of a monoatomic liquid is about the same as for a solid at high temperature. Okay, so it's given by the following formula where C sub V equals to 3 times the Boltzmann constant divided by the molecular weight. Okay, and this is called the Dulong and Petit formula. Okay, and the mean molecular speed, so basically, as I mentioned before, we're going to substitute the mean molecular speed in the y direction. We're going to substitute that by the sonic velocity. Okay, so we're going to replaced by the sonic velocity v sub s. Okay, and the characteristic length, or let's say lambda substituted by the average distance between two lattice planes, right? So that's going to be v over n to the 1/3 power. Okay, so if we substitute these all back into our formula up here, what we get is the following. We get the thermal conductivity for a liquid now equals to 3 times n over v 2/3 times kappa times v sonic. Okay, so this is an important formula based on, let's call this the Brigmann's formula. Or Brigmann's equation. And surprisingly, the experiment shows rather good agreement. Experiment shows rather good agreement to the formula. Except that the numerical coefficient 3 is too high. So the numerical coefficient too high. Okay, so a better agreement. So a better agreement would be the thermal conductivity equals 2.80 times N over V 2/3 the Boltzmann constant times the sonic velocity. Okay. So there is a limitation actually for this equation. So it's limited to densities well above the critical density. And this is because we have the assumption, due to assumption, each molecule only oscillates in a cage formed by nearest neighbors. Okay. Okay, and to complete our discussion here, finally we would show that, give you the information of the sonic velocity in liquid. So the velocity of low frequency sound is given by V sub s equals to the square root of Cp over C sub V times partial pressure, partial density at constant temperature. And the partial P, partial rho at constant temperature may be obtained from isothermal compressibility measurements. Okay, and Cp to Cv is very nearly unity for liquids, except near the critical point, obviously. Okay, so that ends our discussion. So basically, Brickman actually uses the result that we have derived previously for the dilute gas, which is right here, right? Okay, so this is the equation that we have derived for thermal conductivity in dilute gases, and the only thing that he changes is based on the assumption that molecules are arranged in cubic lattice. Okay, so the characteristic distance for a collision is going to be changed to the volume per molecule. okay, or the 1/3 power of that. And the characteristic velocity is going to be changed to sonic velocity, okay. And also using the Dulong and Petit formula to get the constant volume heat capacity for liquid, finally we get to the formula of the Brigmann's equation, except that Brigmann's equation actually overestimates the coefficient, right? So in reality, probably a 2.8 as our coefficient would be more close to reality. Okay, and do remember that this formula is limited to densities well above the critical density, and that's because we have the lattice and oscillated cage assumption here. Okay, so it's rather very packed. Okay, and finally we give you a formula for the velocity of sound, so you can actually calculate stuffs using the Brigmann's equation.